Please join me in welcoming to the Distinctive Voices podium, Dr. Jason Brown.
Thank you very much. Okay, I'm going to talk about the connection between mathematics and music. I was a musician when I was younger. Then I got hooked on mathematics, and at some point I needed to choose between being a mathematician and being a musician. And I chose the safer gig. I became a mathematician. But things come around, and that's going to be the story behind the talk this evening. Well, let me tell you a little bit about mathematics and music. The connection between mathematics and music dates back to at least ancient Greece, where Pythagoras and his entourage placed music and mathematics on the same high pedestal. Now, we'll see that mathematics can interact with music in a number of different ways that I'm going to touch on. The first one is what we need to do is understand the physics and the physiology of sound and music. Music is inherently encoded in mathematics and in physics, and our physiology, for some reason, is particularly suited to discovering the physics and the mathematics that's inherently there. Our bodies and our ears and our minds are built to recognize the mathematics that lies there. We'll also understand the roles of patterns, transformations, and ambiguity in music. And we'll examine the inherent constraints and assumptions of music composition. All of us, whether we listen to music or we write music, have some inherent assumptions that we make. And part of the role of the mathematician is to point out the assumptions that we have and to break them in a significant way. Now, I have found that very few popular musicians will admit to any use of mathematics in their work. I call this the Tommy Lee syndrome, where what you want to do is, as a musician, you want to appear as unschooled as you possibly can. And I think this is a detriment to musicians, because in my opinion, musicians use more mathematics when they do their music than practically any other profession, including accountants. There is so much mathematics that is inherent in the music that they play and in the music that they listen to. I will mention, as a Canadian, one musician in particular, Joni Mitchell, and I think you probably own rights to her as well, because I think she's in California for the last 30 or 40 years. But Joni Mitchell is well known for her guitar playing, and in particular the songs that she writes, she often tunes the guitar strings for each song in a different way. And this opens up new possibilities for her when she plays her music. But she's written, I think, in about 80 different guitar tunings. And you think, how could someone remember all those different tunings? Well, she remembers it in a very mathematical way. And I don't think she recognizes it in that sense, but what she does is she uses a mathematical sequence of numbers to keep track of her special guitar tunings for her songs. Most people who retune their guitar remember the notes of the strings. But because she has so many, what she does is remember the bottom string, and she remembers how many semitones up the next string is from the previous one. So for instance, for the Big Yellow Taxi, which is a D-A-D, F-sharp A-D tuning, she remembers that as a 7-5-4-3-5 tuning. And that's what's stuck in her head. So what I garner from this is that inherently there is some mathematical component to the way she thinks about her music. Now, pure tones are created by an object moving rapidly back and forth in a medium. Pure tones are modeled by sine and cosine curves. And I have to tell you that this is something that I try to bring to high school students everywhere. High school students hate learning trigonometry. There's only one thing they probably hate worse than trigonometry is logarithms. And if you're one of those people, hold on to your hats because you're going to see both of them here. Trigonometry, and in particular sines and cosine curves, are the basis for music. And somehow we're set up to hear those and appreciate those. So everyone should know that trigonometry is not something that's purely theoretical. It's inherently part of our lives every day. Now, more complex tones are linear combinations of sines and cosines. That means that if you have pure tones, they add up to give you the tone that you're listening to in a very mathematical way. Okay, now I'm just going to see if I move away. Can you still hear me? Okay, good. Okay, so I can roam a little bit. I'm not tethered to the spot there. The speed of a pure tone is called its frequency, which corresponds to its pitch. And the pure tone also has an amplitude, which corresponds roughly to the loudness. Between frequency and pitch, it's very closely related. Higher frequencies correspond to higher pitches. The correlation between amplitude and loudness is a little bit more tenuous, but basically, the larger the amplitude, that's the higher that the sine wave goes up and down, the louder that it is. So I've written down a function there. You'll notice not only is there a sine curve there, but there's a pi in there. Because what you need the pi for is to make sure that it repeats as often as you want it to repeat. So I won't go into the details, but this may be your worst nightmare from high school. On the other hand, you may say, things are beginning to make sense. I wish someone had told me about this. Okay, how our ears and brains interpret sound is really quite complex. So I want to talk about something called beats, and this has to do with how piano tuners tune their piano strings. Typically, for a piano, under each note, there are 3 strings that are to be tuned in unison. And what they typically do is they tune one of the strings as precisely as they can, and then they tune the other strings to the first string. Now, how do they do that? Well, they do it by listening. And you would think, how can you tune something like a frequency by listening? But what they hear are beats. So I'm going to show you what they are, and then explain to you why they're so mathematical. So what I'm going to do is, typically, if you play 2 notes at the same time, you hear them as 2 notes as an interval. So if I play these 2 notes, you hear 2 notes there. That's a perfect fifth, a perfect fourth. Now, the strange thing is if I play 2 notes that are very close together, you will not perceive them as 2 notes. What you'll perceive them as a single note that has a wobble. So have a listen to this. Listen for the wobble as I bend one note up to the other one. Even if I go above. Did you hear the wobble? Now, what the wobble is, something called a trigonometric identity. Now, if trigonometry isn't bad enough for students, they hate the trigonometric identities, which are proving the left side is equal to the right side. But we're hearing a trigonometric identity whether you're mathematical or not. So this is what you're hearing. You are hearing that the sine of one number, A, plus the sine of B, can be expressed in another way. Now remember, the sine of something is a tone that we hear. So on the left-hand side, we hear 2 tones, A and B. But this says what's true is that it's equal to twice sine of the average times cosine of some half difference. And the thing is that the sine of the average is the one tone that you hear. The cosine of the half difference is giving the wobble. So we hear the math that's there. Even if you don't know any math, you hear the trigonometric identity. So what I drew was a picture there. If I took something that repeats at 440 hertz, that means 440 cycles per second and 443 cycles per second, you can see when I've drawn the picture of what it looks like, you can see the wobble that's there. And that's what you're perceiving. Actually, the wobble, the number of times you hear it wobbling per second, tells you the difference in the frequencies. And so the tuner listens to the wobble. When it disappears, they're in tune. As noted by the ancient Greeks, notes from melodic instruments are typically made up of a fundamental or a main note, along with integer multiples of the fundamental frequency. Such multiples are called harmonics, and their presence and amplitudes gives each instrument its characteristic sound. I'm having a microphone malfunction here. Okay, so let me just give you an example. Here's a single note. Here's the same note, and I cut the string in half. That's exactly twice the frequency. And if I cut it in a third, you get another harmonic. Now, all of those harmonics, even though I've produced them explicitly here, if I play a single note, there are harmonics. All those harmonics are built into that one note. They're all part and parcel of it. The loudness of each of the harmonics relative to one another gives each instrument its timbre. So a guitar string sounds different from a clarinet not because of the harmonics that are present, but because of the relative loudnesses. And again, we recognize that, and we hear them as being different instruments. If I play you a clarinet, you will recognize that as being different from a guitar string because primarily of the difference in the loudnesses of the harmonics. Now, there are many ways that have been proposed to create scales. And what is a scale? Mathematically, we're not too happy with having a continuous amount of options. You can produce any kind of frequencies. You can produce 443 hertz. You can produce 443.1 hertz. You can produce any sound that you would like. But as humans, we like to have things easy to understand, easy to carry around. And that's called discretization, making things into packages, into steps. And so what you do is you take the continuous number of frequencies and you break them up into a scale. You omit some in order to have a stepwise sequence of them that you can remember. Now, what the Greeks did, they invented a scale called the Pythagorean scale based on frequencies whose ratios form nice small fractions. So when you listen to a note, twice the frequency is an octave, which is probably the most harmonious interval that you can listen to. And in fact, when men and women sing together and think they're singing the same note, they're not. What they're hearing or singing are notes that are octaves apart. And that's because we're inherently, across cultures, built to recognize that kind of equivalence. And in mathematics, that's an actual kind of equivalence that you can describe mathematically with things called congruence classes, etc. Now, other intervals of, that's an interval of 2, an interval of 3/2 is a perfect fifth, which is the next nicest interval. And in fact, most of rock and roll depends on that one interval as being the crucial one. They call the power chords because they're based on the fifths. There are fourths, which aren't as common in rock and roll music, but it's a nice sounding interval. And in fact, they based a scale based on all small fractions. Now, you may look at some of the fractions there and say, well, 243 over 128 isn't a small fraction. But I'll say, yes, it is, compared to some others. So it's all relative. But relatively speaking, they're not that large. Now, but there were problems with that scale in that some of the harmonics of a tone weren't in the scale. Now, there's something wrong with having objects that you could produce musically that wouldn't be part of the structure that you're looking at. Moreover, not all the semitones were the same size. And even worse, trying to change keys was a mess. So they had to decide what to do about this. Now, this is an interesting thing that musicians, by and large, hate mathematics. But the answer to the scale problem was decided once and for all mathematically rather than musically. So what happened was the Pythagorean and other scales were thrown out in favor of equal temperament, in which the octave at twice the original frequency is divided up into 12 equal steps, semitones, such that the ratio of any two tones is equal. So this is a mathematical answer. And what happens is that if you start the original frequency, you say you call it F0, you go up 12 steps. Now, every time you go up a step, you multiply by R. So if you go up to an octave, you have to multiply by R, 12 steps, 12 times. So you get F0 times R to the 12th is twice the frequency, F0. When you cancel it out, you find out this ratio that you need for your semitones has to be the 12th root of 2. Now, I often go on talk shows on radio and people call in. You'd be surprised, but people get angry if they don't get to talk mathematics on the radio. I have found this out. They actually get angry. But I've been asked by people on the air, what's your favorite number? And I say it's the 12th root of 2. They don't believe me, but of course, for mathematics, that would be my favorite number. So the 12th root of 2 is about 1.06, and without it, you really can't do any of the music that we do now. And with it, you can do things like you can change keys in the song, and it won't sound bad. So it was a mathematical approximation. Of course, what you lose then are all the perfect intervals. You lose 3/2, because you can't write that in terms of powers of 2 to the 1/12. You lose 4/3. But what you do is you get approximations, and the approximations are close enough that it's acceptable. So an applied mathematical solution to a musical problem. Now, one of the nice things about being a math professor or a professor at a university is you get to choose the things that you want to do. Maybe it's the only perk. I don't know. I haven't thought about it that much. But it's certainly one of the perks to be able to choose your research projects. So I've been able to bring together my music and my mathematics. And often I will just sit down and think about questions that are musical in nature, but I'm looking for a mathematical solution. And often I find no one has asked those kind of questions. So one thing that has been looked at to some extent, what about blue notes? So I'm going to play you an example. I'm hoping that the volume is going to work. I'm going to play you one of the songs that the Beatles played. They didn't write it. It's called Mr. Moonlight. You remember I think it's off Beatles 65. It was written by someone else. The only good feature of the song is the one opening note that John shrieks. So I'm going to play that for you.
Mr. Moonlight.
Okay. So what I wanted to find out is I thought about that, and I had a couple questions about the notes played there. But what note is he singing? Well, John sings, the whole song is in the key of F sharp. He's singing a note of frequency 920 hertz. I can check that on my computer. Now, the problem is, why is he singing 920 hertz? Because it's between two notes. An A is 880 hertz, and an A sharp is 932 hertz. So why is he out of tune? He's a good enough singer. He shouldn't be out of tune. So the thing is that good blues singers, when they sing by themselves, they don't sing equally tempered. Because you would think, how can they keep in their mind the 12th root of 2? Count up the steps. But what they hear naturally, you'll be surprised. People think I keep the 12th root of 2 in my head, but I don't. So when singers sing, they hear those nice small intervals. They hear the 3/2. They hear the 4/3. And that's what they sing without having the tyranny of having equally tempered instruments play along with them. Because when they play along, they have to sing equally tempered. So when they sing by themselves, they don't sing the equally tempered scale. They sing the just scale, which is pretty close to Pythagorean. And the third, the just third, is a small fraction, 5/4, times the frequency of the tonic, the bass note. An F sharp has a frequency of 740 hertz, and 5/4 times 740 is 925, which is very close to what John sings. So what he is singing, he's singing like a proper blues singer, and that's the note that he's producing. Now, I had another question. I want to ask, what makes the difference between singing a sweet note in a ballad and singing a note that sounds rock and roll? Of course, people are doing things with their throats and their mouths to produce the sounds, but inherently, can you tell something by looking at the frequencies? What are they doing subconsciously? So, in fact, we learn a lot more while looking at the spectrum, which is the frequencies that they're produced, not only the fundamental, but all the harmonics. Such a decomposition, you can break it down by doing something called a Fourier transform. This will come up much later in the talk again. This Fourier transform says that, as I told you before, when you have these sine and cosine curves that add up to give you the complex tone that you hear, a single note, there is mathematics that says, okay, we can pull it apart into each one of the strings, each one of the curves. That's called a Fourier transform. It's something you might learn in first-year calculus. When people described the research that I had done, one of the newspapers, they didn't understand a Fourier transform. So what they said, Dr. Brown using a mysterious operation. So they made it sound like I went, woo. So no, it's not like that. It's real mathematics. I want to ask the question is, what's the difference? So let's compare John singing the open of Mr. Moonlight and Paul singing Hey Jude. I had to find a single note without any instruments there so I could separate it out, and these were the best I could find. So here's John singing Mr. Moonlight, the opening.
Mr. Moonlight.
Okay, and you look, I've shown you the frequencies there, and notice the little peaks. And that indicates across the bottom are the frequencies, the amplitudes, the loudnesses are how high each peak is. Now, underneath I've sampled the first note that Paul sings on Hey Jude, which is a much different sounding, sweeter note.
Hey Jude.
Okay, so if you look at it, what I noticed was the following. What we see is that the harmonics of Paul's sweet opening are multiples of the fundamental. And notice the fundamental, the low note, this is on your right-hand side, most of it is at the bottom. That's the loudest part, the fundamental. But when you look at what John sang, he's really singing a perfect fifth. That not only is the fundamental lower than the fifth, but the fifth is much louder. So what people are doing when they're constricting their throats is they're emphasizing other harmonics, not the fundamental. And in particular, it's almost like they're singing a chord, two notes at the same time. Okay, now, another question was posed by that famous mathematician, Sir Paul McCartney, back in the 60s. So I read a lot of Beatles stuff, and something struck me when I read one of the interviews that the Beatles had done. They had interviewed Paul and John and asked them, what's the best rock song ever written? Does anyone know? Okay, let's not all see all the same hands. Okay, he said the greatest rock song was Long Tall Sally by Little Richard. And I think it is a great rock song. If you hear the Beatles do it, the kind of energy they generate is incredible, the thrill of it. So I was wondering, Paul McCartney is such a good musician, why did he consider that to be the ultimate rock song? And moreover, I even went back a step and said, well, Long Tall Sally is an example of a sequence of chords, a chord progression called the blues. And the blues are a particular sequence of chords. They're almost always 12 bars long. Certain chords last for certain lengths, but it's always the same. And yet, people devote their whole lives to playing that same 12 bars, and people spend their whole lives listening to the same 12 bars. So why is that chord progression so good? And so I thought that was a mathematical question, that I have this underlying premise that if something seems so right in music, it's mathematical. So the question that I asked myself, and I hadn't seen anyone ask it before, why are the blues so fundamental, so damn good? And I wrote an article about this, and I'll explain it. Now, to begin with, we're going to play an example of the blues for you. But to do it, you've got to do it correctly. Okay. 1 triplet, 2 triplet, 3 triplet. Thank you. I feel like the Clark Kent Superman thing. So let me explain to you what I came up with. I had to think of what makes the blues so thrilling. And I thought, what would be a good model for it? Well, what in life is thrilling? And I thought one of the ultimate thrills is to go on a roller coaster. People find a roller coaster. So I thought, what about if you wanted to model a roller coaster musically with a sequence of chords? You wanted it to be exciting. Well, I would imagine if I were building a roller coaster, it would have three parts to it. It would have a beginning, a middle, and an end, each of roughly the same length. So furthermore, what you want is to build the thrill. So you want it to accelerate as you go through the roller coaster. Well, what's the easiest way to accelerate mathematically? Is to double the pace. So if we start with the beginning of having one chord lasting for the beginning part, you would double with 2 equally spaced chords in the middle and 4 equally spaced chords at the end. Now, if you say you work back, well, what's going to be the length of it? Say the 4 chords at the end, because they're the fastest ones, are each 1 bar long. Then the 2 chords in the middle are each 2 bars long, because we're increasing the pace. The beginning one is 4 bars long. So what you come up with are 7 chords and 12 bars. We're beginning to build the blues. Now, of course, what you want is you want each chord out of the 7 to be different from the previous one. Otherwise, you haven't changed anything. So I work in an area in mathematics, in addition to math and music, called discrete mathematics, that has to do with objects called networks or graphs. Pictures involving points and lines joining them. So what I saw was it came up in this case. So what I do is I drew the blues as a circle with the points indicating the chords, and I drew a line when they're next to one another, time-wise. So there's 7 of them, and what you want to do is you can think of the chords that we're going to use for these points are colors. You're going to paint them with the color. And typically, in blues, you have chords like the 1 chord, and the 4 chord, and the 5 chord. Now, how many chords would you need to represent the blues in this way? That means in this cycle with 7 points, how many colors would you need to color the points in such a way that if points are joined by a line, they have to get different colors? Well, you can easily see 2 colors aren't enough. Try alternating, you'll find out the first point and the last point have the same color. It means you can't do a blues with only 2 chords. You need 3. Now, if you want the most basic one, you would ask, can I do it with 3? And the 3 chords you would use would be the 1 chord, which is the base of the key, the 4 chord, which is next most interesting, and the 5 chord, which is the most exciting out of the 3. So, making a few more deductions, what I found out was that there's only one solution to this. And the only solution for this roller coaster, musically, is the blues. And that's, to me, exactly why the blues are the way they are. There's very little variation, only minor variations, because they're so perfect mathematically and so thrilling. Okay, so here's another interesting question. What makes the diatonic scale, that means the major scale, of 7 notes so special? If you notice the sequence of semitones, that's 2 up, 1, 2, 2, 2, 1. Now, in Western music, if you have to choose 7 notes, why don't you choose another arrangement of semitones and tones? Why is it that one? So I'm going to give you an answer. This isn't mine. This is one that some music theorists came up with, but I think it's very pretty, and it will help you when you invite guests over for dinner. So here's the problem that you have. You have a dinner table, a circular dinner table, with chairs around it. You're not going to take away any chairs because you have a different number of guests coming every week. It would just be a pain. You've got only a smaller number of guests coming, and you want to seat them around the table, but you don't want them clumping because they'll talk about you, and then they'll mutter to themselves. They'll talk about dinner, what wasn't right, so you want to spread them out so you don't have that happening. So you want to spread around K people around a table with N chairs as evenly as possible. Now, you have to talk about what evenly as possible means. Certainly, if there were 12 chairs around the table and you had 6 people, there's no question what you do, right? You seat them every every second chair. But what happens if you have 7 people around a table with 12 chairs? Then it becomes a little bit more dicey. So you need a proper definition for what it means to be evenly distributed. Now, I won't write down the definition because it's a little bit complex, but they have defined it, what it means to select k points around the circle from n possible points, such that they're as evenly distributed as possible. And they call this property being maximally even. If you look at this example, the black ones are the seats. Well, you can see this is not a good arrangement. This is not maximally even. The people on the left side, sorry, I guess it depends on which side. On one of the sides, I get mixed up because it's backwards and forwards. On one of the sides, you can see there's 4 black dots with only 1 white one in between them. They're clumped. They're going to talk about you. So that's not a good choice, but this one's a better choice. There's a little bit of clumping. There has to be because you've got 7 around the table. But it seems pretty good. And this one's, according to the definition, maximally even. Now, if you look at the top point, the top black one that's next to the white one, think of that as being the note C. And think of each one of these being semitones. What you would get is C, D, E, F, G, A, B, C when you come back again. Exactly the major scale. And in fact, what they show as a result was that no matter how many seats you have around the table and how many people you have to seat around the table, there's exactly one solution. Well, there's always many solutions by rotating the people. Take the pattern and move it around. That obviously is the same pattern. And that corresponds to starting the major scale on different notes. But that's the only solution. So for 7 around a table of 12, there's only one solution. And that's the major scale. Now, what about 5 people around a table with 12 chairs? Well, that's the pentatonic scale. It sounds like 6 notes because I played the octave at the top just to end it off. But it's 5 notes. Pentatonic scale is the scale on 5 notes that everyone uses in the blues, and that's used in the Orient. Again, it's cross-culturally the scale to use for 5 notes. What about 6 notes? For 6 notes, it's called the whole tone scale. And for 7 notes, it's the major scale. Now, if you think about that, which one was the least appealing of those? It was probably the whole tone scale. And it's interesting because the whole tone scale is the perfect one. It's exactly, everything is exactly 2 semitones apart. So this is the other premise that I want to put forward, is that we as humans like things to be almost perfect. We don't like perfection, but if it's really close to being perfect, that's ideal. Now, what about maximally even rhythms? So instead of looking at it as semitones, what about if you look at beats where you might play? Well, the maximally even rhythms are some of the most famous rhythms in the world. Bossa novas, rumbas, and a number of other famous international rhythms are maximally even. So we're going to play you a little bit of a bossa nova. Okay. 1, 2, 3, 4. So that does not flow nicely. And that's what I was playing on the guitar is the bossa nova beat. 1, 2, 3, 4, 1, 2. And that's maximally even. Flows really nicely. Now, here's again, so the maximally even are nice, the rhythms, because they're as close to perfect, but not quite perfect. What happens if you go another step over and you say, I'm not happy with close to perfect, I want something a little edgier. And you find if you move a little bit away from maximally even and be a little bit imperfect from there, you get something that has even more interest, even more grit. So we're going to play you a rhythm. Now, in mathematics, if you're really lucky and really smart, you get a theorem named after you. But I think what beats that is having a rhythm named after you. So this rhythm is called the Bo Diddley rhythm, after Bo Diddley. I don't know if he invented it, but it's at least attributed to him. And what he plays is something that's almost maximally even, almost the bossa nova, except he moves just 1/8 note. So it's almost as perfect as maximally even, but it has a lot of grit to it. Okay, we ready, guys? 1, 2, 3, 4, 1, 2, 3, 4. Now, for a second, I'm going to move over from playing something live for you. How many of you have seen visual paradoxes like the one with the urns and the faces? Okay? They're great. Well, there are other ones. If you've, there's an artist called M.C. Escher who did a lot of famous paintings and sculptures. And one of the things he loved were mathematical paradoxes. So if you look at this one, look at this staircase and travel around it. And you can see that you can always climb even when you get back to where you started. So there's some sort of paradox inherent there. You shouldn't end up, if you're always climbing, back where you start. But you do. So someone named Roger Shepard used harmonics to build an oral representation of this infinitely climbing staircase. So an oral stairway to heaven, but long before Led Zeppelin. So I'm going to play it for you. He based it on 12 notes from the chromatic scale. There'll be the regular 12 notes, but remember, a note can be made up of harmonics. And he carefully chose the harmonics for each one of them using a sine curve. Now, rather than get into the details, listen to it. I'm going to play it to you once, and you should agree it's 12 notes, each of the chromatic notes rising. Okay? Now, what I'm going to do now is I'm going to play you the same ones. I'm going to take the same sound file, paste it twice after itself. Now, when it comes back for the 13th note, it's the original first note. I guarantee you it is. But see if it, so it should drop down to the beginning. But see, I'm going to count it for you. Does the 13th note really sound like it's dropped from the 12th note? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. The 25th should be low. So, and as many times as I listen to it, I still can't figure out what's going on just by listening. It's still a trick, like looking at the urns and the urn and the faces. Now, patterns in music are the glue that holds songs together. Transformations, which is inherently what mathematics often does, on patterns, allows for variety while maintaining consistency in the listener's minds. Composers have known this for centuries. So I'm going to play you a bunch of patterns. I Walk the Line. The opening is a sequence of patterns, some going up and moving, and then transformed by transposition, it's called, moved up a certain number of semitones, inverted to go back down. And one of the chords in that sequence is not typical of a country song. Country songs, guitar players for country bands are typically known as 3-chord Charlies, because in country music, you have the 1 chord, the 4 chord, and the 5 chord, and that's it. And for some of the players, they almost go brain dead if they can just play those same 3 chords after one. He introduces a new chord there that should sound out of place, but it's the patterns that hold it all together. 1, 2, 1. So I think it all held together. Let me just move this up a little bit. Okay, the next one that I'll play for you is in jazz. Duke Ellington used lots of different patterns. Okay, ready? 1, 2, 3, 4. hear the patterns weaving its way through it. Now, I'm going to show you another pattern. Often in rock and roll, you like to build songs around a guitar riff. And a guitar riff is simply a little tidbit of music played on the guitar. And often they do something to it to create interest. Now, I'm going to talk about a guitar riff by those mathematicians, Foreigner, and the song Hot Blooded. So here's what they started out with. This was the basis of the riff. Now, if you listen to that, how interesting can that sound? But they took that same pattern, then they moved it up. They transformed it by moving it up 4 notes, 5 semitones. And not only that, what they did was essentially put a mirror on the middle line in the staff there, on the B line, and reflect it. So instead of going down, it goes up. So 2 transformations they did there. And they also transformed it time-wise by moving it back a beat. So they've got 3 transformations going on at the same time. Then they have the B chord, where they move it up 7 semitones. So this one pattern sounds like this. 1, 2, 3, 4. Okay, so I think Foreigner did a pretty good job with next to nothing, but it's the mathematics that makes it good. Okay, now, ambiguity. I want to talk about ambiguity in mathematics, in music. Ambiguity in real life typically isn't a good thing. If you've got a significant other and she plays guitar, and suppose she plays a song for you that she's written. She says, "How do you like?" And you say, "Well, I'd like nothing better." That kind of ambiguity is likely to get you in the doghouse for at least a couple of days. On the other hand, in mathematics, ambiguity is a good thing. We embrace ambiguity to translate a problem from one area of mathematics into another, or to look for an alternate model of a theory. Now, in music, composers embrace ambiguity for interest. The fact that it's ambiguous, whether it's music or in poetry, is an advantage that you can come back and look to. And it's the reason that things sound fresh. So, here's another research problem that I gave for myself. I knew that the Beatles came to America and they needed to write a great song to break the American market back in '64. They were big in England, but all these songs that they had written in England, Capitol Records wouldn't release here. They thought they weren't commercial. So they had to come up with what they felt was their big song. And I liken it to if you're a professor at a university, finding out you have a conference in 6 months. It's the most important conference of your entire life. And by the way, you had better come up with your most brilliant research paper for that one, a new paper. Well, how many people could manage that? Well, the Beatles managed it for some reason to come up with what I consider one of their best songs. So I wanted to figure out why was I Want to Hold Your Hand such a great song. Now, if you look at the song, it's a very interesting song. So I'm going to have to tell you a little bit about the musical background. Typically, a rock song has blues notes. Those are notes outside of the key, outside the major scale, like the flat third and the flat seventh, and it's what gives it its power. Almost every rock song does. This is a rock song, and a great rock song, but it has only melody notes from the major scale. Typically, what songs have only notes from the major scale? Nursery rhymes. So how did this escape being a nursery rhyme and become a great song? Well, what I claim is it's the mathematics that they put into it. So, as well, when I listen to I Want to Hold Your Hand, every time I listen to it, I really get excited. There's something that boils up inside me. You hear it, and it moves you. So what I think is, when I listen to the song, it sounds fresh every time. And I've listened to it, I'm certain, over 100 times. Every time it sounds fresh. The freshness, I think, is the mathematics that's in there. So let me explain. But before I do, let's play it. Okay. Okay, so we're going to go 2 verses, and the bridge, and then the verse out, right? Here we go. 1, 2, 3. Oh yeah, I'll tell you something that you'll understand. When I say that something, I wanna hold your hand. I wanna hold your hand. I wanna hold your hand. Oh, please say to me, you'll let me be your man. And please say to me, you'll let me hold your hand. I wanna hold your hand. I wanna hold your hand. And when I touch you, I feel happy inside. It's such a feeling that my love I can't hide, I can't hide, I can't hide. Yeah, you got that something I think you'll understand. When I say that something, I wanna hold your hand. 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 Thank you. Now, I want to talk the opening stumble, which sounds like a stumble. What makes it sound so good? It's only the 4 chord to the 5 chord, the 2 most basic chords besides the 1 chord, the tonic chord. It should sound ordinary. But the key thing is what they did. So we have an assumption as a listener. A listener listening to music likes to find beat 1 because they can center themselves on beat 1. So you want to find beat 1 amongst the music that goes by. Now, how do we find beat 1? Well, we have an assumption. The assumption that everyone makes is without having any other clues, a song begins on beat 1. So this should have sounded like this: 1 and 2, 4, 1 and 2. But the Beatles were smarter than that. They sat down, took out a pen and paper, and said, we're going to do a mathematical transformation to it. We're going to apply f of x equals x minus 3 to it, and move it back 3/8 notes. And so, instead of it being 1 and 2, it's 1, 2, 3, and 4, and. And I have a friend who's played Beatles music for 40 years. He told me it took him years to figure out how they did that. So just something as subtle as that, moving it back by a transformation, can create mystery, and it sounds fresh every time because you can't figure out where beat 1 is until a couple bars later when he comes in with the vocals. And no matter how much you know what he does, the Beatles do, John does, it still tricks you every time. It can't help but trick you. And that's ambiguity. Now, the other question that I wanted to ask is the bridge to the song, and when I touch you, I feel happy inside. It's such a beautiful bridge. It's very interesting. It somehow fits the song perfectly, and yet it's interesting. So I wanted to find out, why is that bridge so good? So I actually wrote an article in Guitar Player magazine. It's called The Mathematics of John's Left Hand. So I'm sure other people reading were wondering what's going on here. But what happens is, why is that bridge so good? Well, what they do is they modulate. They change the key, which is, again, something interesting. It's a mathematical transformation to move things up. They move it up 5 notes. But as well, if you look at it, what I noticed was the following. It's in the chorus, I want to hold your hand, is C to D to G to E minor, C to D to G. The chords for the bridge are D minor 7 to G to C to A minor, D minor 7 to G to C. The thing is that a D minor 7, that first chord, is the same thing. It's got a D, F, A, C. If you ignore the bottom note, the D, it's an F chord, an F, A, C. So, with a different bass note. So if you look at that, really they're the same pattern. Not only did they move it up 5 notes, but it's exactly the same pattern in different keys, of the 4 to the 5 to the 1 to the 6 to the 4 to the 5 to the 1. Exactly the same pattern, but they've hidden it by moving it up. And as well, what they did was stretch it. And even if you look at the melody, they did things that they're very similar, the melodies, not shape-wise, but time-wise between the two. So they did this naturally. I don't think they did it inherently by thinking about it, but they did it naturally because they're great music writers. But the best music writers are mathematical. Now, the thing that I wanted is, okay, so they did change that, and the D minor 7, perhaps they did this all subconsciously. But the D minor 7 isn't the right chord mathematically, and that bothers me. But clearly, George Harrison is playing the D minor 7. I can tell that. Paul McCartney's playing a D in the bass. So maybe they did it subconsciously, but I wanted to know, when they wrote it, could one of them have been thinking of the real chord, the F chord, the perfect mathematical chord? So I'm going to show you a little bit of the Beatles playing it on the Ed Sullivan Show. Look at John's left hand when they come to the opening of the bridge.
When I touch you, I feel happy inside. It's such a feeling that my love, I can't hide.
Playing the F chord. Now, why would John play a different chord from George Harrison? It'd be so unusual to do that. The only reason he would do that is because when he wrote it, he thought of the mathematical perfect chord, and that was the F chord. And he didn't care. He said, to hell with the other guys. I'm playing the chord that's right there. OK, let me give a little quote from George Harrison from his autobiography, I, Me, Mine. He never did well in math in school. And he wrote the following. All those logarithms and square roots, and algebra was a terrible thing. X plus 3 over z equals y. Now you can tell if you know mathematics, he's really lost there. I will have learned Chinese or Sanskrit sooner than that. It seems to have made sense to the academics, the intellectuals. Algebra, I have no idea what it means or where it came from. But algebra to me has nothing to do with reality. I watch it now on Open University and I still can't connect. What's the most interesting thing here? Here's a man in the twilight years. He could do anything he wants. He's got as much money to do whatever he wants. He's sitting home and turning on the television to watch Open University math lectures that are being sent out over the airwaves. Why on earth? The only reason I can come up with is he was inherently mathematical. He didn't get mathematics from school, but that doesn't mean he's not mathematical. And he knew there was something there that he was missing. OK, now, there's Chuck Berry. George loved playing some mathematical guitar tricks, playing patterns of 3 against patterns of 4. And I played that at the beginning when I played Chuck Berry. It was all of that is patterns of 3 against patterns of 4. Chuck Berry, I assure you, is no great mathematician, and yet he does something brilliant mathematically. To play patterns of 3s against patterns of 4s, it's like rubbing your tummy and patting your head at the same time. You've got different patterns going on. And it gives a wild sound to it. And I noticed when Chuck Berry does that, what does he do? That's exactly the moment when he does his duck walk across the stage. Why? He's so moved by the mathematics of it, how cool it sounds, he's got to move. So if you have math students, get them to move. This is the trick. OK, so, and you'll hear it a little later, but in the solo that, I wrote another article for Guitar Player magazine about the famous solo that George Harrison plays in A Hard Day's Night, and I found proof. It's so perfect that I felt that he must have cut the speed down in half and recorded it down an octave. And I found proof that he did that. But what he plays in the song, the patterns, these are 16th notes, but they're patterns of 3s. And he liked it so much and heard it in his head, even though he couldn't play it, he said to the producer, cut the tape speed down in half, I have to play this way because it sounded right to him, it sounded excited to him. Amazingly, he realized while he recorded at half the speed and when they turned back the speed back up, it was very fast and exactly what he wanted to play. He had to play it live a few months later. So he had to have the nerve to actually do that, which he did. Okay, but what you need when you do that is you need an escape hatch. What you need is a way to get out. You can't just do the patterns of 3 against patterns of 4 unless you calculate the least common multiple. You have to know where you end up. How many patterns of 3 will land up with patterns of 4? Well, how many 3s end up with 4s? This is a least common multiple problem. And it's 12. So they do it naturally. Interesting side note, Roger McGuinn, the lead guitarist of the Byrds, was a passionate follower of George Harrison's guitar work. And he also has patterns of 3s against patterns of 4s. Listen to his guitar work in Mr. Tambourine Man, the lead guitar. Listen to him turn, turn, turn. All the patterns of 3s. So I claim that really probably what he had in common with George Harrison was a love of mathematics. Okay, now, here's where I come. I hope I'm creative. We're just going to go a little bit longer. I want to come to the point where I tell you how I became famous. I'm a mathematician. I'm used to be working in obscurity. And not the obscurity that's in every state in the United States, the obscurity in Nova Scotia. And it was 2004. I knew it was the 40th anniversary of A Hard Day's Night. And that brought me back to one of the most famous openings in rock and roll. So we're going to play you a little bit of the song. Oh, we'll skip that. We'll skip that. Yeah. Okay. Okay, ready? 1, 2, 3, 4. It's been a hard day's night, and I've been working like a dog. It's been a hard day's night. I should be sleeping like a log. But when I get home to you, I find the things that you do will make me feel I'm alright. But when I get home to you, I find the things that you do will make me feel I'm alright. When I'm home, everything seems to be right. When I'm home, feeling you holding me tight. Tight, yeah. It's been a hard day's night, and I've been working like a dog. It's been a hard day's night. I should be sleeping like a log. But when I get home to you, I find the things that you do will make me feel I'm alright. You know I feel I'm alright. You know I feel Thank you. Okay. So I'm going to finish off by telling you the story of A Hard Day's Night and my part in that. So here's what the George Martin said. We knew it would open both the film and the soundtrack LP, so we wanted a particularly strong and effective beginning. The strong guitar chord was the perfect match. Well, it seems to have closed the discussion about the chord, but should it have? Okay, I think that's good. Here's the first one. First finger, a bar chord across the 3rd fret. Does that sound right? Probably not quite right. The next one is this. Oh, sorry. Probably sounds a little closer. And here's another one that I won't play for you. It involves all 3 Beatles playing. But how do you decide? I mean, is it up to everyone to figure out? Yeah, I think I'm just locked up in here. You got that? Thank you. I'll put that down. Thanks. Boy, it's hard to manage all this electronics. You know, at one point, I remember when I used to give talks, if I brought colored chalk, the audience would get excited. Multimedia. Okay, now you have to have everything hooked up. Okay, so what I did was the following. I thought, there must be a scientific way to figure out how the Beatles played the opening chord and figure out which one of these different transcriptions is the right one. So what I did was I took a snippet of the chord and I ran it through something called the Fourier transform, which I mentioned before, which will pick apart the frequencies that made it up. Now, of course, the frequencies are not just the notes they played. It would be harmonics. It would be anything that rattled in the room. So what I found 30,000 frequencies, which is almost enough to give up. But what I could tell were the relative loudnesses, and that was a saving grace for it. So what I keyed in on, because I could demark them, the loudnesses, I looked at the 48 largest frequencies of largest amplitude, and I got this. And I tell people, this is a beautiful picture. Okay? To me, it is. It says a lot. Now, if you look at this, I don't know if you can't read the numbers probably back where you are, but I know some things. For instance, there's 110 hertz. That's an A. at a certain amplitude. There's a bunch of them around 150 in the first column, and one of them is particularly loud. It's got an amplitude of 0.175. The other ones are about smaller than half of that. So I began to make deductions that amongst these loudest frequencies must be the notes that the Beatles played. There would undoubtedly be some harmonics in there, etc., but I could start making some deductions. So I began to make some deductions, but what you have to do is you have to convert from the frequencies to notes. How do you do that? Well, you've got that 12 through to 2 looming around, and you have to figure out the notes. What do you have to do to undo powers? You need logarithms. So I had to apply the function 12 times the log base 2 of x over 220. The 220, I just had to pick a note that's a certain A. And then I got semitones. And now what I found out is this is how many semitones the notes that were being played were away from a certain note, an A220. I noticed something very interesting that no one else had noticed before. The Beatles recorded A Hard Day's Night on the 9th take. They should have retuned their guitars in between. They're out of tune. Because, of course, you should be an exact integer number of semitones away from any given note if you're in tune. But they weren't. So some of the things are actually quite badly out of tune, but it adds to the interest in the chord. Another thing that when I rounded them to the closest notes, I got the following. The 2s and the 3s indicate which octave they're in. But there's an A2, a bunch of D3s, F3s, etc. Many of the tones are not surprising. But notice all the versions that I played were incorrect, that everybody's been playing for years. That low G that everybody plays on the guitar isn't there. They're hearing another G that's higher up, and because they're trying to decide with their ears and their minds what's being played, they hear the bottom G because they know the key of the song is G. So there's got to be a G in there. But there's no G in there. And only the mathematics will tell you that. Now, what I begin to do is to make deductions. That loud D that I mentioned before, it's a single note. It's much louder than anything else. It has to be Paul playing it on the bass. And often people, when they transcribe that note, even if they get a D, they get it in the wrong octave. But I can tell where it is. Now, I begin to try to ascribe the notes to George Harrison's beautiful 12-string Rickenbacker guitar. I believe Rickenbacker is a company out here in California. They made one of the first 12-string guitars, and he got one of the very first ones. And he loved it, and he played it on the opening track. But it doesn't work. And what you notice is you've got those 3 F3s, but no F4. And when you play an F3, a certain F on a 12-string guitar, you have to play the F4, because they're tuned in octaves. So he couldn't have played that on his 12-string. And then I'm stuck. Well, maybe John played it. He could play one of the F3s. Can't play more than one. He's only got one possible place to play it. Maybe Paul somehow plucked an extra note. That's an extra F3. But where's the third one coming from? So I was really stuck. And at this point, I almost gave up. One night, I had an epiphany. And the epiphany was that I had an assumption. And this is one of the great things about being a mathematician. You have to, at some point, examine your assumptions. The assumption I made was that George Harrison was playing the guitar chord there, and that only the Beatles, if George Harrison was accompanied by anyone, it would be the Beatles with their guitars. But maybe there was more than just the guitars of the Beatles on the track. And that began to unravel. Remember I mentioned a piano has typically 3 notes under every string? Well, those 3 F3s could have come from a piano note. So what I did immediately, I ran down in Halifax into a piano store, and I began sticking my head inside the pianos to count the strings. So the manager, of course, came over to talk to me. And I explained to him what I was doing, so I guess he was okay with that. But pianos have 3 strings under each note near the top. In the middle, there's 2 strings under each note. And the bottom, there's just 1. So I began to ascribe these to the piano. And undoubtedly, the piano was played by George Martin, who was a piano player, the producer. And finally, I have one more note for John Lennon. So this was my transcription of it. And that's what it looks like and how it appears in Guitar Player magazine. So in the end, there's a mix of piano and guitar. And if you look at the amplitudes for the guitar notes and the piano notes, it's almost perfect. He did it by ear. And it's because he mixed them so perfectly together that almost everyone can't distinguish the piano in the mix. But if you listen to it now, I guarantee now that you know there's a piano in there, you'll hear the piano. And what about the strident guitar chord? Because that's what the producer, George Martin, said. It was a strident guitar chord, and yet he played the piano on the chord. So George Martin, which I call Martin's axiom, which is a little mathematical joke, which unless it's a very mathematical crowd, it just goes over people's heads. He said the following: it shouldn't be expected that people are necessarily doing what they appear to be doing on records. He likens it to filmmaking where all sorts of effects are carried out in the background in order to create illusions. So I want to tell you one irony, and I'll almost be done. I guess sometimes in life you can enjoy a great irony. It's by one chance at fame. It hit the media. It got into the national paper in Canada to begin with, National Post. So they print the article all about me. And whose picture do they put there? Not my picture. My brother in Toronto someone goes up to my brother in Toronto and says, I read the article about your brother in the National Post. He looks exactly like Paul McCartney. So where this led me is, it led to a book that I wrote, Our Days Are Numbered, led to a CD that I did. And one other thing, I'll just end off that mathematics, even in its both basic form, is an essential and useful tool in pop music. I'll play you one thing. The Wall Street Journal came up to interview me because of this. And when they came up, I said to them, well, you're sending a videographer with you. How about if we play a song that I wrote in the style of the Beatles using mathematical principles? They said, sure. And then I hung up the phone and said, oh, no, I don't have a band. So I had to go get a band. And luckily for me, there's a singer in Halifax named Hal Bruce who does a lot of Beatles work. He plays in the Cavern in London. But in Liverpool, but he sounds just like the Beatles. So here's a song I wrote called A Million Whys. See if I wrote it to be a song that if the Beatles had written it, it would be a hit. That was my aim, with some mathematics. So have a listen.
Got a million reasons.